So today we're looking at how to simplify more complex exponential expressions. So expressions that have a little bit more going on than just one or two things at a time. And just like when you have really complex normal expressions where you have a bunch of addition, subtraction, multiplication, and division going on, you have a certain order of operations to follow, right? Most people call it PEMDAS, about steps to do and how to get the right answer. Well, the same holds true when you're simplifying these types of expressions. You have kind of 3 steps you do in order to whittle it down to as low as you can get. And they are, right here, distribute over any parentheses. So if you have that exponent outside of parentheses, you're going to multiply that to the other exponents inside there to get rid of that first. Then you're going to combine any multiplication you have. So if you have 2 bases that are the same, when you multiply them together, you just add the exponents to get that new base, or to get that new term, something we did in the previous video. And then perform any divisions, the last step, kind of like the reverse of the second step. When you have 2 bases that are the same and you divide them, you subtract the exponents to get the new term. So let's see how this plays out in some examples here. So for the first one, we have a 3 right up here that we can distribute to each of the inside terms there. And again, my first step is to distribute over the parentheses. So that's my first thing I'm going to do, is I'm going to take that outside 3 and distribute to everything inside there. Now remember, distributing an exponent means you're going to multiply it to the other exponents. So that to the 4th, 4 times 3 is 12, so that's going to be 2 to the 12th. That x to the 9th, 9 times 3 would give me 27, and then 5 times 3 would give me y to the 15th. So that's my first set gone. My second set doesn't have any exponent on the outside. There is no exponent up here in the corner that I have to distribute, so I can just ignore it. I can just rewrite that second part because there's nothing to distribute there. It's just as it is. Okay? So with no exponents left to distribute, I'm going to go to my second step, which is combine any multiplication I have. So let's look for any multiplication I can combine. Well, I have 2 to the 12th. I have 2 to the 3rd. Both have a base of 2. So I'm going to add their exponents, and that'll be 2 to the 15th. I have x to the whopping 27th. Here's x to the 1st. So together it's going to be x to the 28th. And lastly, I have my y. So y to the 15th, y to the 8th. That's going to give me a whopping y to the 23rd. Because I'm adding their exponents. And that will be all I need to do. That's my final answer. That is my expression fully simplified as much as I can. I cannot do anything more to it until I know what x and y are. So that's as low as I can go. It's kind of like simplifying a fraction almost. So if we tack on some division in there, things get a little bit more complicated, but not too much, because there was no division in that one we just did. My first step, though, is still the same. Take the outside exponents and multiply them to the inside exponents of their respective parentheses before you do anything else. So I see a 5 out here, same style we had before. I'm going to distribute that 5 to all those exponents inside those parentheses. So we're going to go through this here. 16 to the 1st is now 16 to the 5th. Remember, if there is no exponent on the number, you assume there's an invisible 1 on there. 5 times x to the 3rd, so it'll be x to the 15th. Y is y squared, so now it's y to the 10th, because 5 times 2 is 10. And then z to the 4th is now z to the 20th, because 5 times 4 is 20. Then I'm just going to take my other part here and bring it down. And then I'm going to bring the bottom of my fraction into play. So now I have what I had before, and I'm going to combine using multiplication. Remember, division is saved for the very last step, so right now it's multiplication. Well, I'm going to hold off on the 16 and the 2 right now. I'm going to put those over here. So 16 to the 5th, 2. Okay. We'll do stuff with those later. Then I have some x's I can make. So I have an x to the 15th. I have an x to the 7th. Together that'd be x, and the exponents would be 22. a y to the 10th, a y to the 9th, together to be y to the 19th. And z to the 20, z to the 1st, so together to be z to the 21st. And then down here I have my 4x to the 8th, y to the 3rd, z. Give myself some more space here. So now there's no more multiplication I can do, so now my last step is to perform any division there. Now the reason I kept my 2 and my 16 separate is because when I do the number portion of this, I can see right here, this 2 and this 4 can cancel a little bit. So what I'm going to do is I'm going to keep 16 to the 5th as it is for right now. This 2 is going to cancel with this 4 and make that a 2. Just like I would a normal fraction, 2/4 would cancel down to 1/2. So I'm going to put that 2 on bottom here. So all I just did is canceled the 2 on top with the 4 on bottom, just like if it was a normal fraction, because it is still a normal fraction. So that's where that goes. And I'm going to move that 2 actually a little bit if I can, so that it's not in the way while I write my other stuff. So I have x to the 22nd, I have x to the 8th. Because I'm dividing, I'm going to subtract their exponents. So it's going to be 22 minus 8. And it is important to do the order correctly. So it's the top exponent minus the bottom exponent. So 22 minus 8 would give me x to the 14th. Y to the 19th, y to the 3rd. Subtract those exponents. You get 19 minus 3, which would give you 16. And z to the 21st over z to the 1st would just give me z to the 20th. And so far, that's pretty much a lot of the work done. There is still a tad bit more you can do, and I'll show you that in a second. But for right now, this would be mostly acceptable to, I would think, most teachers, unless you're in college, in which case they probably want you to do this next step a little bit, and some of your high school teachers might as well. So let me show you one extra step that's kind of hidden in here. Okay? And it has to deal with my numbers, 16 to the 5th and 2. So this is a little bit of an extra piece of information here. 16 and 2 don't look like they can cancel, but they actually can. Because even though it's 16 to the 5th, we can still kind of transform it a little bit. So I'm going to take that 16 to the 5th, I'm going to think to myself, well, what really is 16? 16 is really just 4 times 4, right? 16 is the exact same thing as 4 squared. So let me write it like that. Let me take 16 and write it as 4 squared to the 5th. Because that's what that means, right? 16 to the 5th is 4 squared to the 5th, because 4 squared and 16 are the same thing. All I did was replace this with 4 squared. And now I can see that, well, this right here, I know how to do that. It's a power to a power. That's just going to be 4 to the 10th. But even more, 4 itself can be done this way as well, because 4 itself is 2 squared, right? So I could replace the 4 with 2 squared to the 10th. And once again, I have a situation where I have an exponent to an exponent. I'm like, okay, I can do that. That's going to be 2 to the 20th. So what I've done is I've taken 16 to the 5th, and I've willed it all the way down to 2 to the 20th. So what I can do is take this expression and say 2 to the 20th, x to the 14, y to the 16, z to the 20th, all over 2. But now I see even more than that. What I realize is there's 22's on top, 2 to the 20th, so 22's. And there's a single 2 on bottom. So I can cancel like I would with normal exponents. Because that 2 on bottom, remember, is a 2 to the 1st. Even though you don't see the 1 there, it's an invisible 1. It's 2 to the 1st. So I can do my little division trick, and I can say that this is 20 minus 1 would be 2 to the 19th, x to the 14th, y to the 16th, and z to the 20. So fully reduced would be that right there. You have actually no fraction left over because you can manipulate the 16 and whittle it down piece by piece by piece into a 2 format. So that's a little bit of extra simplifying there. It's a little bit more complex, and I might make a video on just that later. But for right now, it happens few and far between at the grade level we're at right now that I'm not going to bother with going too much into that. So we're going to go ahead and on to the next part here, which is a little bit about special types of exponents. So the first special type of exponent we're going to look at is 0, because it's a pretty simple one. Anything to the 0 power is simply 1. Doesn't matter how big or small, whether it's a fraction or a decimal, it's variable or number. Anything to the 0 power is always going to be 1. So if I write down, say, 10 to the 0, that's 1. If I say 7 to the 0, that's 1. If I say negative 4 to the 0, that's 1. If I say x to the 0, that's 1. So no matter what I can think of or write down, if it's to the 0 power, it's 1. If I take a big, long chunk of something, write this down real quick down here. If I take x to the 4th times y to the 20th, z to the 51st, and then 10,008, or 1008, and if I make all this to the 0 power, it's 1. Doesn't matter what anything on the inside is. If it's all taken to the 0 power, that 0 gets distributed. Anything times 0 itself is 0, so all those exponents become 0. So the entire thing just boils down to 1. Okay? So that's one of the simple special exponents, is that anything to the 0 power is always going to be 1. Big, small, whole number fraction, decimal variable, always going to be 1. Now, why is this the case, though? Why does that happen? Why are we so sure that's always going to be 1? Well, it's kind of an offshoot of a property we did in the other video, the division property. So if I have 5 to the 9th over 5 to the 9th, well, we know what to do here, right? 5 to the 9th over 5 to the 9th means you're going to subtract the exponents, 9 minus 9, and you'll get 5 to the 0. Whoops, not 50. You're going to get 5 to the 0, because 9 minus 9 is 0. Okay, that's good. Make that 0 down here a little bit more. Whoops, not that 0, that 0. So far so good. But look here, this is the same number divided by itself. 5 to the 9th divided by 5 to the 9th. I have the exact same number divided by itself. And there's another property of division, right? Anything divided by itself is 1. Big, small, decimal fraction, variable, number. Anything divided by itself is 1. So we know that automatically this is going to be equal to 1, because it's the same thing divided by itself. Well, if it's equal to 1, and it's equal to this, that means these two must be equal to each other as well. So 5 to the 0 must also be equal to 1. And you can perform this trick with any number or variable as well. As long as it's the same exponent on top and bottom, and as long as it's the same base, it's always going to come out to be 1, because it's essentially the same number divided by itself. So that's why anything to the 0 power is 1, is because it's kind of an offshoot of the division property of exponents. So that one's the simple one. Anything to the 0 power is 1. The next one's a little bit trickier. It has to deal with negative exponents. So the rule for negative exponents is that any negative exponent is the reciprocal of its positive counterpart. So for example, 4 to the negative 6th is just 1 over 4 to the 6th. X to the negative 12th is 1 over x to the 12th. 9 to the negative 1st is 1 over 9 to the 1st, or just 9. So negative exponents are the flipped form of their positive counterparts, essentially. So if you have a 4 to the negative 20th, you have 1 over 4 to the positive 20th. So you flip the number from top to bottom, or even from bottom to top. So as another example, if I had this, if I had 5 to the negative 3rd, that is 1 over 5 to the 3rd. If I have 1 over 5 to the negative 8, that is just 5 to the 8, or 5 to the 8 over 1 if you want to be very specific. But you flip it both ways. So if it's like the first one, you flip it so it's on bottom. If it's already on bottom, then you flip it so it's on top. So you flip the position and make the exponent positive if it's a negative exponent. And once again, the reason why this works is because it's an offshoot of the division property for exponents. So if we take this case here, let me erase my example here so I have some room. If we take this case here, 3 to the 2nd divided by 3 to the 5th. If I write that out, again, we know by division property that this is going to be 3 to the 2 minus 5, which is going to be 3 to the negative third. That's how we know, it just by the division property of exponents, that's what we know it's going to end up as. But if I actually write this out a little bit, this is 3 times 3 over 3 times 3 times 3 times 3 times 3. Get my fraction bar there. Well, if we do what fractions do, and that is cancel things that are the same, we have those 3 cancel, those 3 cancel, so I'm left with a 1 on top, because remember, I don't cancel make a 0, I cancel make a 1. So I have a 1 on top, and I have 3 3's on bottom, or I have 3 cubed, because 3 3's is 3 cubed. So this is also equal to 1 over 3 cubed. But it's also equal to 3 to the negative third. Well, if they're both equal to the same thing, if this is both equal to the same thing, then that means these two must be equal to each other as well. So 3 to the negative third must be equal to 1 over 3 to the third. And once again, you can do this with any number or variable, and you always get the same setup. That 1 over the positive version is equal to just the negative version of the exponent. Now, normally, when we do our work, we don't really like to have negative exponents in our final answer. It's kind of like leaving a fraction unsimplified. If you have a negative exponent, it's good form to actually turn it into a positive exponent for your final answer. Okay? Because, again, it's like leaving a fraction unsimplified. It's just not a very good or nice thing to do. So we usually do not want negative exponents in the final answer of our problem, even though sometimes we might have to deal with them during the problem. So let's take a look at some of these here where negative exponents might pop up. In this first one here, let's do, again, our order of operations. So there's no exponents to distribute. We're good there. There's no real multiplication to distribute, so we're good there too. There's no real multiplication to do. So we're going to go straight to the division part. So let's do this. 6 divided by 2 is 3. X squared over x to the 7th. Well, that is 2 minus 7, so that'd be x to the negative 5th. 9 over 3, so that's 9 minus 3, so that'd be y to the positive 6th. Now, normally that'd be all well and good, but I have an x to the negative 5th, and I really don't want to have a negative exponent in there. So what I could do is one of two things. There's two ways you could write your answer here. The first way is to simply say it's 3 times 1 over x to the 5th, because remember the negative exponents are flipped, times y to the 6th. That's one way you could write it. It's kind of a messy way of writing because you have kind of a fraction nestled in between two whole numbers. So even though it's mathematically accurate, it doesn't really look all that nice. So what normally people would do is they would take it and make it one giant fraction. So they'll say 3 y to the 6 on top, because those were both positive exponent numbers. And then the bottom, they'll just put x to the 5th. So instead of keeping it as its own little fraction, they're just going to make it one giant fraction, and because the x to the negative 5th was a negative, it's going to flip to be on the bottom, so it's now a positive exponent. Because once that flip occurs, it changes to a positive exponent, and now this would be my final answer. So even though both are correct, this way would be the more appropriate way of writing your answer. Let's try one more here where the negative is already given for us. So in this case, negative 5 minus 6, so x to the negative 5 minus 6. Well, negative 5 minus 6 is x to the negative 11th. Here it's 3 minus 2. Well, that's just 1, so that's just y. That's easy. Here is 1 minus negative 4. So once again, 1 minus negative 4. Well, a minus a negative makes a plus, right? So it's actually like 1 plus 4. So it's actually just z to the 5th. So you have to be careful when the negatives start on bottom in the problem because they can kind of mess up your fraction division rule. Or your exponent division rule, I should say. So now we're back to just having one pesky negative exponent, so we're going to put that on the bottom of our answer rather than leave it on the top. So we're going to write our positive exponent numbers on top. So those are both my positive exponent variables. And on the bottom, I'm going to put my negative exponent down there so it becomes a nice positive. That way I can show my answer as a nice version with all positive exponents. and no messy negative exponents. So with negative exponents, the object is to flip them from where they're at in your final answer, so that you don't have to have any negative exponents in your final answer. So that's some more advanced exponent combinations for expressions. Hope you enjoy the video. Have a good day.